Hi guys, so I'm back for another video, and for this video I'm going to explain the chapter summaries or the overall summaries. So let's start. Chapter 1, Exploring the Network. Networks and the internet have changed the way we communicate, learn, work, and even play. Networks come in all sizes. They can range from simple networks consisting of 2 computers to networks connecting millions of devices. The internet is the largest network in existence. In fact, the term internet means a network of networks. The internet provides the services that enable us to connect and communicate with our families, friends, work, and interests. The network infrastructure is the platform that supports the network. It provides the stable and reliable channel over which communication can occur. It is made up of network components including end devices, intermediate devices, and network media. Networks must be reliable. This means the network must be fault-tolerant, scalable, provide quality of service, and ensure security of the information and resources on the network. Network security is an integral part of computer networking. Regardless of whether the network is limited to a home environment with a single connection to the internet or as large as a corporation with thousands of users. No single solution can protect the network from the variety of threats that exist. For this reason, security should be implemented in multiple layers using more than one security solution. Network infrastructure can vary greatly in terms of size, number of users, and number and types of services that are supported. The network infrastructure must grow and adjust to support the way the network is used. The routing and switching platform is the foundation of any network infrastructure. This chapter is focused on networking as a primary platform for supporting communication. The next chapter will introduce you to the Cisco Inter-Networks Operating System or iOS, used to enable routing and switching in a Cisco network environment. Chapter 2, Configure a Network Operating System. Cisco iOS is a term that encompasses a number of different operating systems which runs on various networking devices. The technician can enter commands to configure or program the device to perform various networking functions. Cisco iOS routers and switches perform functions that network professionals depend upon to make their networks operate as expected. The services provided by the Cisco iOS are accessed using a command line interface or CLI, which is accessed by either the console port, the AUX port, or through the SSH or telnet. After connecting to the CLI, network technicians can make configuration changes to Cisco iOS devices. The Cisco iOS is designed as a model operating system, which means a network technician must navigate through various hierarchical modes of the iOS. Each mode supports different iOS commands. Cisco iOS routers and switches support a similar model operating system, support similar command structures, and support many of the same commands. In addition, both devices have identical initial configuration steps when implementing them in a network. This chapter introduced the Cisco iOS. It detailed the various modes of the Cisco iOS and examined the basic command structure that is used to configure it. It also walked through the initial settings of a Cisco iOS switch device, including setting a name, limiting access to the device configuration, configuring banner messages, and saving the configuration. The next chapter explores how packets are moved across the network infrastructure and introduces you to the rules of packet communications. Chapter 3, Network Protocols and Communications. Data networks are systems of end devices, intermediary devices, and the media connecting them. For communication to occur, these devices must know how to communicate. These devices must comply with communication rules and protocols. TCP or IP is an example of a protocol suite. Most protocols are created by a standards organization such as the IETF or IEE or IEEE. The Institute of Electrical and Electronics Engineering is a professional organization for those in the electrical, engineering, and electronics fields. ISO, the International Organization for Standardization, is the world's largest developer of international standards for a wide variety of products and services. The most widely used networking models are the OSI and TCP or IP models. Associating the protocols that set the rules of data communications with the different layers of these models is useful in determining which devices and services are applied at specific points as data passes across LANs and WANs. Data that passes down the stack of the OSI model is segmented into pieces and encapsulated with addresses and other labels. The process is reversed as the pieces are then encapsulated and passed up the destination protocol stack. The OSI model describes the processes of encoding, formatting, segmenting, and encapsulating data for transmission over the network. The TCP or IP protocol suite is an open standard protocol that has been endorsed by the networking industry and ratified or approved by a standards organization. The Internet Protocol Suite is a suite of protocols required for transmitting and receiving information using the Internet. Protocol Data Units or PDUs are named according to the protocols of the TCP or IP suite: data, segment, packet, frame, and bits. Applying models allows individuals, companies, and trade associations to analyze current networks and plan the network of the future. Chapter 4: Network Access. The TCP or IP network access layer is the equivalent of the OSI data link layer or layer 2 and the physical layer, layer 1. The OSI physical layer provides the means to transport the bits that make up a data link layer frame across the network media. The physical components are the electronic hardware devices, media, and other connectors that transmit and carry the signals to represent the bits. Hardware components such as network adapters or NICs, interfaces and connectors, cable materials, and cable designs are all specified in standards associated with the physical layer. The physical layer standards address three functional areas. First is the physical components, second, frame encoding technique and signaling method. Using the proper media is an important part of the network communications. Without the proper physical connection, either wired or wireless, communications between any two devices will not occur. Wired communication consists of copper media and fiber cable. There are three main types of copper media used in networking: unshielded twisted pair or UTP, shielded twisted pair or STP, and coaxial cable. The UTP cabling is the most common copper networking media. Optical fiber cable has become very popular for interconnecting infrastructure network devices. It permits the transmission of data over longer distances and at higher bandwidth data rates than any other networking media. Unlike copper wires, fiber optic cable can transmit signals with less attenuation and is completely immune to EMI and RFI. Wireless media carry electromagnetic signals that represent the binary digits of data communications using radio or microwave frequencies. The number of wireless-enabled devices continues to increase. For this reason, wireless has become the medium of choice for home networks and is quickly gaining in popularity in enterprise networks. The data link layer handles the exchange of frames between nodes over a physical network media. It allows the upper layers to access the media, and controls how data is placed and received on the media. Chapter 5: Ethernet. Ethernet is the most widely used LAN technology today. It is a family of networking technologies that are defined in the IEEE 802.2 and 802.3 standards. Ethernet standards define both the Layer 2 protocols and the Layer 1 technologies. For the Layer 2 protocols, as with all 802 IEEE standards, Ethernet relies on the two separate sublayers of the data link layer to operate: the logical link control or LLC and the MAC sublayers. At the data link layer, the frame structure is nearly identical for all bandwidths of Ethernet. The Ethernet frame structure adds headers and trailers around the layer 3 PDU to encapsulate the message being sent. There are two styles of Ethernet framing: IEEE 802.3 Ethernet standard and the DIX Ethernet standard, which is now referred to Ethernet 2. The most significant difference between the two standards is the addition of a short frame delimiter SFD and the change of the type field to a length field in the 802.3 Ethernet 2 is the Ethernet frame format used in TCP or IP networks. As an implementation of the IEEE 802.2 or 3 standards, the Ethernet frame provides MAC addressing and error checking. The Layer 2 addressing provided by Ethernet support unicast, multicast, and broadcast communications. Ethernet uses the address resolution protocol to determine the MAC address of destinations and map them against known IPv4 addresses. Each node of an IPv4 network has both a MAC address and an IPv4 address. The IP addresses are used to identify the original, source, and final destination of the packet. The Ethernet MAC address are used to send the packet from one Ethernet NIC to another Ethernet NIC on the same IP network. ARC is used to map a known IPv4 address to a MAC address, so the packet can be encapsulated in an Ethernet frame with the correct Layer 2 address. ARP relies on the certain types of Ethernet broadcast messages and Ethernet unicast messages, called ARP requests and ARP replies. The ARP protocol resolves IPv4 address to MAC addresses and maintains a table of mappings. On most Ethernet networks, end devices are typically connected on a point-to-point basis to a Layer 2 full duplex switch. A Layer 2 LAN switch performs switching and filtering based only on the OSI data link layer or Layer 2 MAC address. A Layer 2 switch builds a MAC address table that it uses to make forwarding decisions. Layer 2 switches depend on routers to pass data between independent IP networks. Chapter 6: Network Layer. The network layer or OSI Layer 3 provides services to allow end devices to exchange data across the network. To accomplish this end-to-end transport, the network layer uses four basic processes: IP addressing for end devices, encapsulation, routing, and de-encapsulation. The Internet is largely based on IPv4, which is still the most widely used network layer protocol. An IPv4 packet contains the IP header and the payload. However, IPv4 has a limited number of unique public IP addresses available. This led to the development of IP version 6 or IPv6. The IPv6 simplified header offers several advantages over IPv4, including better routing efficiency, simplified extension headers, and capability for per-flow processing. Plus, IPv6 addresses are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. This dramatically increases the number of available IP addresses. In addition to hierarchical addressing, the network layer is also responsible for routing. Host requires a local routing table to ensure that packets are directed to the correct destination network. The local table of a host typically contains the direct connection, the local network route, and the local default route. The local default route is the route to the default gateway. The default gateway is the IP address of a router interface connected to the local network. When a host needs to forward a packet to a destination address that is not on the same network as the host, the packet is sent to the default gateway for further processing. When a router such as a default gateway receives a packet, it examines the destination IP address to determine the destination network. The routing table of a router stores information about directly connected routes and remote routes to IP networks. If the router has an entry in its routing table for the destination network, the router forwards the packet. If no routing entry exists, the router may forward the packet to its own default route if one is configured, or it will drop the packet. Routing table entries can be configured manually on each router to provide static routing, or the routers may communicate route information dynamically between each other using a routing protocol. In order for routers to be reachable, the router interface must be configured. To enable a specific interface, enter Interface Configuration Mode using the Interface Type and Number Global Configuration Mode command. Chapter 7 IP Addressing. IP addresses are hierarchical with network, subnet network, and host portions. An IP address can represent a complete network, a specific host, or the broadcast address of the network. Understanding binary notation is important when determining if two hosts are in the same network. The bits within the network portion of the IP address must be identical for all devices that reside in the same network. The subnet mask or prefix is used to determine the network portion of an IP address. IP addresses can be assigned either statically or dynamically. DHCP enables the automatic assignment of addressing information such as IP address, subnet mask, default gateway, and other configuration information. IPv4 hosts can communicate one of three different ways: unicast, broadcast, or multicast. Also, blocks of addresses that are used in networks that require limited or no internet access are called private addresses. The private IPv4 address blocks are 10.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. The depletion of IPv4 address space is the motivating factor for moving to IPv6. Each IPv6 address has 128 bits versus the 32 bits in an IPv4 address. IPv6 does not use the dotted decimal subnet mask notation. The prefix length is used to indicate the network portion of an IPv6 address using the following format: IPv6 address / prefix length. There are three types of IPv6 address: unicast, multicast, and anycast. An IPv6 linked local address enables a device to communicate with other IPv6 enabled device on the same link and only on that link or subnet. Packets with a source or destination link local address cannot be routed beyond the link from which the packet originated. IPv6 linked local addresses are in the FE80/10 range. ICMP is available for both IPv4 and IPv6. ICMP-v4 is the messaging protocol for IPv4. ICMP-v6 provides the same services for IPv6 but includes additional functionality. After it is implemented, an IP network needs to be tested to verify its connectivity and operational performance. Chapter 8: Subnetting IP Networks. The process of segmenting a network by dividing it into a multiple smaller network spaces is called subnetting. Every network address has a valid range of host address. All devices attached to the same network will have an IPv4 host address for that network and common subnet mask or network prefix. Traffic can be forwarded between hosts directly if they are on the same subnet. Traffic cannot be forwarded between subnets without the use of a router. To determine if traffic is local or remote, the router uses the subnet mask. The prefix and the subnet mask are different ways of representing the same thing, the network portion of an address. IPv4 subnets are created by using one or more of the host bits as network bits. Two very important factors that will lead to the determination of the IP address block with the subnet mask are the number of subnets required and the maximum number of hosts needed per subnet. There is an inverse relationship between the number of subnets and the number of hosts. The more bits that are borrowed to create subnets, the fewer host bits that are available. Therefore, there are fewer hosts per subnet. The formula 2^n, where n is the number of host bits remaining, is used to calculate how many addresses will be available on each subnet. However, the network address and broadcast address within a range are not usable. Therefore, to calculate the usable number of addresses, the calculation 2^n-2 is required. Subnetting a subnet or using variable length subnet mask or VLSM was designed to avoid wasting addresses. IPv6 subnetting requires a different approach than IPv4 subnetting. An IPv6 address space is not subnetted to conserve addresses. Rather, it is subnetted to support a hierarchical logical design of the network. So, while IPv4 subnetting is about managing address scarcity, IPv6 subnetting is about building an addressing hierarchy based on the number of routers and the networks they support. Careful planning is required to make best use of the available address space. Size, location, use, and access requirements are all considerations in the address planning process. After it is implemented, an IP network needs to be tested to verify its connectivity and operational performance. Chapter 9: Transport Layer. The transport layer provides transport-related services by dividing data received from an application into segments, adding a header to identify and manage each segment, using the header information to reassemble the segments back into application data. UDP and TCP are common transport layer protocols. UDP datagrams and TCP segments have headers added in front of the data that include a source port number and destination port number. These port numbers enable data to be directed to the correct application running on the destination computer. TCP does not pass any data to the network until it knows the destination is ready to receive it. TCP then manages the flow of the data and resends any data segments that are not acknowledged as being received at the destination. If the application data needs to be delivered across the network quickly, or if network bandwidth cannot support the overhead of control messages being exchanged between the source and the destination systems, UDP would be the developer's preferred transport layer protocol. UDP provides none of the TCP reliability features. The application developer decides the transport layer protocol that best meets the requirements for the application. It is important to remember that the other layers all play a part in data network communications and influences its performance. Chapter 10: Application Layer. The application layer is responsible for directly accessing the underlying processes that manage and deliver communication to the human network. This layer serves as the source and destination of communications across data networks. The application layer applications, services, and protocols enable users to interact with the data network in a way that is meaningful and effective. Delivery of data over the network can be requested from a server by a client or between devices that operate in a P2P arrangement. In P2P, the client or server relationship is established according to which device is the source and destination at that time. Messages are exchanged between the application layer services at each end device in accordance with the protocol specifications established and use these relationships. All of these elements work together at the application layer. The application layer enables users to work and play over the internet. Chapter 11. Build a small network. In order to meet user requirements, even small networks require planning and design. Planning ensures that all requirements, cost factors, and deployment options are given due consideration. An important part of the network design is reliability, scalability, and availability. Supporting and growing a small network requires being familiar with the protocols and network applications running over the network. Protocol analyzers enable a network professional to quickly compile statistical information about traffic flows on a network. Information gathered by the protocol analyzer is evaluated based on the source and destination of the traffic as well as the type of traffic being sent. This analysis can be used by a network technician to make decisions on how to manage the traffic more efficiently. Common network protocols include DNS, Telnet, SMTP, POP, DHCP, HTTP, and FTP. Network must also protected from network attacks. Network attacks can be classified into three major categories: reconnaissance, access attacks, and denial of service. There are several ways to protect a network from attacks: authentication, authorization, and accounting, a firewall, and then to protect network. Okay, that's all for today. Thank you for watching.